To continue our lecture from last time, let's recall the notion of supremum and infimum. So supremum was the least upper bound, infimum was the greatest lower bound. And again, let me illustrate this by these notions by using two examples. I'm going to look at two different sets. One I'm going to call S, and it will consist of all real numbers between 0 and square root of 2. And the set T is going to be a similar thing, except that here we're going to assume that the set is going to consist of all rational numbers between 0 and square root of 2. So notice in the second case, I cannot actually say that x is between 0 and square root of 2 because square root of 2 does not belong to the set of rational numbers. So instead, I'm going to use the same definition in both sets. So set S is larger than a set T. Okay, so and then what I want to do is I want to demonstrate first that the supremum of a set S is going to be a radical of 2, and the infimum of a set S is going to be 0. Okay, so let's do this in two steps. Step number 1, let's look at the infimum. So what does it mean that the infimum of S is 0? It means that, first of all, 0 must be a lower bound on S. And number 2, it means that 0 must not be just a lower bound, but a greatest lower bound. Well, first of all, if I choose any x in the set S, then by definition of S, x must be non-negative. So by definition, any number in the set S is greater or equal than 0. So automatically 0 must be a lower bound because 0 is less than any element of S. So this part 1 is actually trivial. So part 2, I want to demonstrate now that 0 is a greatest lower bound. Now, what does it mean that it is the greatest lower bound? It means that if I move slightly higher than 0, then going slightly higher will give me not a lower bound, but something else. What does it mean that I have something which is not a lower bound? It means that I should be able to find an element of my set below that number which is not a lower bound. And so what I need to do, I need to figure out how to demonstrate that if I go above 0, if I pick any number which is greater than 0, then that number must not be a lower bound. And as we discussed last time, so the procedure here is this. So I can choose any small positive number. If I choose any small positive number, then last time I did an example which showed that if you take an average of two numbers, so in this case, average of 0 and t, which is 0 plus t over 2, so which is t over 2, then the average is always going to fall between the numbers, average of which you're taking. So since t over 2 is an average of 0 and t, this is a number which is greater than 0, less than t. If I chose t to be a small number, then automatically it would be less than a radical of 2. So then t over 2 is between 0 and radical of 2, and so it must belong to the set S. All right, so then t over 2 is a number which lies in the set S and which is below t. So then t automatically cannot be a lower bound because I can find an element of my set which is below that number. So that means that 0 is going to be the greatest lower bound. And so 0 is the infimum of S. We can do a very similar thing to demonstrate that square root of 2 is a supremum. So again, by definition of S, all elements of x must be less than radical of 2. So radical of 2 is clearly an upper bound. How do I show that it is the least upper bound? I do it in the following way. If I move slightly below square root of 2, then the new number that I'm going to get is not going to be an upper bound. And if I can show this for any t below, for any number below radical of 2, then radical of 2 must be the least upper bound. So this is what I'm going to do. I'm going to choose again some small number t greater than 0. And I'm going to consider two numbers, square root of 2 minus t and square root of 2. Square root of 2 minus t is less than square root of 2. And if I take an average of square root of t minus square root of 2 minus t and square root of 2, I should get square root of 2 minus t over 2, which again, by our proof from last time, is going to lie between the numbers, the square root of which, between two numbers, the average of which I have taken. All right. Okay, so then square root of 2 minus t over 2 is less than square root of 2. If t is a sufficiently small number, then square root of 2 minus t is a positive number. So the average then is less than square root of 2 greater than 0, so it belongs to S. So then average is a number that belongs to S, and it is higher than square root of 2 minus t. So that means that square root of 2 minus t, again, it cannot be an upper bound because I can find an element of my set which is larger than it. So that then implies that square root of 2 must be the least upper bound or supremum of S. So again, remember the difference between Q and S and T. T was a similar set, similarly defined set, but it's a set of rational numbers. So then to demonstrate that its enthymon is 0 will be as easy as doing it here for S. We basically follow exactly the same proof and we're done. But to think about the supremum of T, this is somehow more complicated because supremum of T, the supremum of all rationals with squares less than 2, the supremum seems to be square root of 2 again. But square root of 2 is not an element of Q. So then we conjecture that the supremum of T actually does not exist because the number that should be supremum is actually missing. It's not there. Let's try to demonstrate that. So we'll do it in the following way. So I'm going to suppose that the supremum does exist. And I can only talk about suprema that belong to Q because I'm working in terms of a set of rational numbers, so I don't know anything about real numbers. So supremum must be an element of Q. Okay, so it's an element of Q, then I don't know yet what it is. I have three choices. Either that supremum is going to be less than square root of 2, or its square is less than 2, its square is greater than 2, or its square is equal to 2. If I can eliminate all of these three possibilities, then the supremum would not exist. So I'm denoting the supremum by S, and I'm going to consider three cases. Case number 1, S squared is less than 2. So what happens here? If S squared is less than 2, then, so right now we don't know how to do it, but in next lecture, actually, we're going to show that between any two real numbers, I can find the rational number. So S is a rational number, which is also a real number. Square root of 2 is a real number. So then between S and square root of 2, if I live in a set of real numbers, I should be able to find a rational number between them. So when I square those, I can find always a rational number Q, square root of which is going to lie between S squared and 2. So at this point, again, we don't know how to do it, but you have to trust me that that's something that is possible to do. All right, and so then what about Q? Q is a number square of which is less than 2. So q then becomes an element of t. And so q is an element of t. And if q is an element of t, then s cannot be an upper bound because I found an element of my set, upper bound for t, because I found an element of my set which is bigger than this presumed upper bound. So that's contradiction. So s cannot be a supremum of t. Number 2, let's suppose that s squared is greater than 2. I can do exactly the same thing. If s squared is greater than 2, then there should exist a rational number, the square of which lies between 2 and s squared. But if a rational number like that exists, because q squared is bigger than 2, then q must be an upper bound for the set t. But if q is an upper bound for the set t, which is strictly smaller than my supremum s, then again, this is a contradiction because s was assumed to be the least upper bound, and q is a smaller upper bound. So that is a contradiction. So then the only possible choice for s is that s squared is equal to 2, right? It cannot be less than 2, it cannot be bigger than 2, it must be equal to 2. But then square root of 2 is not a rational number. So that means that supremum of t does not exist. If I work in a set of rational numbers with something like this, supremum does not exist. If I work in a set of real numbers, then the supremum exists. Let's do one more quick example. Actually, I'll leave it up to you to verify this. If I define t now in a different way, where I will replace 2 by 4, then of course now x squared less than 4 means that x is less or equal than 2. And in that case, I would ask you to try to show that supremum actually exists and is equal to 2, and infimum is still 0. So from the examples that we just did, we can observe that if I take a set of rational numbers, and I'm not guaranteed that the supremum of that set will exist. In this case, it does exist, but in the previous case, it didn't. While and the reason why it did not exist for x squared less or equal than 2 was that the presumed supremum actually did not belong to the set that we're considering. That is not a problem when you work with a set of rational numbers because it doesn't have any holes. So the assumption then, the conjecture then, is that a bounded set of rational numbers does not have to have a supremum. It may or it may not, while a set of real numbers should have a supremum. And that is a distinction between a set of rationals and a set of reals, one distinction, and that is because certain elements in rationals are missing, then not all bounded sets will have a supremum. So if we work with a set of rational numbers, real numbers, then the following statement is going to be assumed to be true. That whenever I have a non-empty bounded, non-empty subset of a set of real numbers which is bounded from above, then that set does have a supremum. And that supremum is actually a real number. And the same axiom is not valid in Q. So that is again an axiom. This is not some property of the set of reals that you deduce from somewhere, but it is an assumption that we're going to make. And then based on that assumption, we're going to establish a bunch of different facts. And I'm going to begin with the following. So I'm saying any set which is bounded from above will have a supremum. But then it should also be true that any set that is bounded from below has an infimum, right? Because this would be a symmetric statement somehow. The claim is that it's just enough to make an axiom about suprema, and then the statement about infimum will follow. And that is going to be the substance of an X theorem. So here I'm going to suppose that I have a set which is bounded from below, and the claim is that then the infimum exists. So this looks almost like a completeness axiom, except that we're talking about boundedness from below an infimum. So somewhere in the proof I would need to use a completeness axiom. And this is how I'm going to do it. So the idea is that if I have a set of, let's say, set of numbers on the positive side of x-axis, and that set is bounded from above, if I take these numbers, I multiply them by -1, everything will reflect with respect to the origin. And so then the set of -x is going to be bounded from below. And so this is a symmetry that I'm going to utilize. So let's say I have a set S of numbers, and I'm going to consider a set of all minus of all negatives of these numbers. So I'm going to call the set -S would be a set of all numbers, negative of which belong to S itself. So then saying that some x is going to belong to S is equivalent to saying that -x belongs to -S, right? If x is in S and -x is in -S, if x is in -S, then -x belongs to S. So in order for me to use a completeness axiom, I will have to show that the set -S is actually bounded from above, and I have to use here the fact that S is bounded from below. So because S is bounded from below, there must exist a real number such that that real number is a lower bound on S. So that means that every x in S is going to be greater or equal than m. But then if I take this inequality and I multiply by -1, that gives me that -x is less or equal than -m, still for every x in S. So that means that -x is less or equal than -m for every number -x in -s, right? Which means that -s is bounded from above by -m. Okay, so then if -s is bounded from above by -m, then by completeness axiom, -s must have a supremum. And I'm going to denote that supremum as S0. And so from the existence of the supremum, now I have to show that the existence of a supremum on -s, I have to be able to show that there exists an infimum of S. So let's take any number x that belongs to S. Then -x of that number belongs to -s. And because -x belongs to -s, and S0 is an upper bound, is a supremum on -s, it must be true that -x is less or equal than S0. All right, but then if -x is less or equal than S0, again, multiplying by -1, x should be greater than -S0. So for every x in S, we see that x must be greater or equal than -S0, so -S0 then is a lower bound on S, right? So what else can I say about -S0? I'm going to try to show that -S0 in fact is the infimum. So if I want to show it is an infimum, then that means that it is a greatest lower bound. If it is a greatest lower bound, then any number above it is not going to be a lower bound. So I'm going to choose any number t which is above this -S0, and I want to show that t is not itself a lower bound. How can I do that? So if t is bigger than -S0, multiplying by -1, S0 is greater than -t. Now remember that S0, the way we defined it, S0 is a supremum of -s, and because it is a supremum of -s, it's a least upper bound on -s. So then, because S0 is greater than minus t, then that means that minus t itself cannot be an upper bound on minus s, right? Because s0 is a least upper bound. And if minus t is not an upper bound on minus s, then I can always find a number minus s such that minus s is bigger than minus t, because minus t itself is not an upper bound on minus s. But now multiplying both sides of this by minus 1, we reverse the sign of the inequality, and we see that element of s, the opposite element to minus s, is s, which belongs to s, and s must be less than t. But if s is less than t, then t cannot be a lower bound because I can find an element of s which is less than it, which allows us to conclude that minus s0 in fact is the greatest lower bound on s. And moreover, if we recall the definition of s0, s0 was supremum of minus s, so I can replace s0 by the supremum of minus s. And so we see that the infimum of s is going to be minus supremum of minus s. So the way to take the greatest lower bound is to invert your set by multiplying it by minus 1, taking its supremum, and then inverting back. Okay, one more theorem here, which is an important property that we will use a few times later on. And that property is this one. If I have two positive numbers, a and b, two positive real numbers, then there must exist a positive integer, a natural number n, such that if I multiply a by a sufficiently large n, then an is going to dominate b. This sounds like it is an obvious property, but actually it relies on the completeness axiom. And if you think about a system of numbers that does not satisfy completeness axiom, then you can show that in some systems of numbers like that, Archimedean property will fail. So we'll prove this by using contradiction. If I want to show that there exists an n such that n is bigger than b, if the Archimedean property fails, then no matter which n, which natural number n I choose, then always an must be less or equal than b. So if an is less or equal than b for all n, then I can form a set of all positive integer multiples of n, call this set S, and then clearly all elements of S are less than b, so that means that b is a bound on S. So that means that S is bounded from above. But because S is bounded from above by completeness axiom, it must have a supremum, and so I'm going to call that supremum S0. Okay, so we're going to work with S0. So S0 is the least upper bound on S, so that means that if I reduce it by any amount, the outcome is not going to be an upper bound. So I'm going to subtract a from S, and S0 minus a cannot be an upper bound because S0 again is the least upper bound. If S0 minus a is not an upper bound, what does it mean? It means that I should be able to find an element of S such that that element is bigger than S0 minus a. Now, all elements in S are integer multiples of a, so I can find n such that S is equal to na. But then, substituting here, na must be bigger than S0 minus a, and I can add a to both sides and factor a to discover that n plus 1 times a must be bigger than S0. Well, but who is n plus 1 times a? S consists of all integer multiples of a, and n plus 1a is an integer multiple of a. So that means that n plus 1a is an element of S. But then what have I found? I found an element of S which is greater than the supremum of S, which is impossible. So this is a contradiction, and therefore the Archimedean property holds. And next time we're going to, as I said, we're going to prove some additional theorems, which in fact will use the Archimedean property.